There was a time when the future of computing seemed to belong to one company. Intel did not build the first personal computer. It did not create Windows. It did not invent the internet. But hidden inside millions of machines was the technology that made the computer revolution possible. A small piece of silicon carrying the Intel name became the brain of the modern PC. It powered offices, schools, laboratories, banks, factories, and eventually the servers that connected the world. By the 1990s, Intel was no longer simply a semiconductor manufacturer. It was an empire. Its processors became faster with every generation. Its factories operated at the limits of physics. Its logo appeared on computers made by companies across the planet, and its famous five-note sound became one of the most recognizable signatures in advertising history. Intel had something its competitors could only dream of. It designed the chips, it manufactured the chips, and it controlled the architecture on which an entire industry had been built. But technological empires rarely collapse because they stop being powerful. They collapse because the world changes faster than they do. When computing moved from desks into pockets, Intel was not ready. When advanced manufacturing became more expensive and complicated, its once unbeatable factories began falling behind. When artificial intelligence transformed graphics processors into the most valuable machines in technology, another company stood at the center of the revolution. Intel had helped create the digital age. Yet by the time the next age arrived, the company that once defined the future was struggling to remain part of it. This is the story of how Intel rose from a small Silicon Valley startup to become one of the most powerful corporations on Earth. How it survived crises that should have destroyed it. How confidence slowly became complacency. And how the empire that placed a computer on every desk was forced to fight for its own survival. In 1968, Silicon Valley was not yet the global capital of technology. It was still a region of orchards, industrial buildings, and ambitious engineers working on machines most people had never seen. But inside Fairchild Semiconductor, a revolution was underway. Robert Noyce had helped turn the integrated circuit from an experimental idea into a practical device. Gordon Moore had recognized a pattern that would define the industry. As manufacturing improved, the number of components placed on a chip would continue to grow at an extraordinary rate. Together, they had helped make Fairchild one of America's most important semiconductor companies. They were respected, they were wealthy, and they were becoming frustrated. Fairchild Semiconductor was controlled by Fairchild Camera and Instrument, an older East Coast corporation whose priorities did not always match the speed of the new silicon industry. Noyce and Moore believed more of the division's profits should be reinvested into research and manufacturing. Instead, they felt the company was becoming cautious. For engineers who could see how quickly electronics were advancing, caution looked dangerously similar to surrender. By 1968, Moore was considering a new opportunity. Most computers still stored information using magnetic core memory, tiny magnetic rings woven together by hand into complex grids. It worked, but it was bulky, labor-intensive, and vulnerable to a technology manufactured directly on silicon. Moore believed semiconductor memory could become the foundation of a new company. He discussed the idea with Robert Noyce during an informal conversation at Noyce's home. The two men had already left one famous laboratory together to help create Fairchild. Now they were preparing to leave Fairchild itself. They were walking away from successful careers because they believed the next opportunity was even larger. On July 18, 1968, Noyce and Moore incorporated their new venture. The first paperwork called it NM Electronics. The name was accurate but forgettable. They eventually chose Intel, a shortened form of integrated electronics. Because a hotel chain already controlled a similar name, they paid for the right to use it. The company still needed money. Arthur Rock, the financier who had helped arrange the creation of Fairchild, backed the engineers again. Noyce and Moore invested their own money, while Rock organized much of the outside financing. Investors were not simply buying a product. They were betting on the men themselves. Almost immediately, Andy Grove joined the company. Grove was different from the relaxed and charismatic Noyce and the quiet, analytical Moore. He was intense, demanding, and obsessed with execution. Noyce could inspire people. Moore could see where technology was moving. Grove would build the discipline required to turn those ideas into an industrial machine. Intel began operations on August 1, 1968, with roughly a dozen employees working from a conference room in an old Union Carbide building in Mountain View. There was no famous logo, no global factory network, no microprocessor. The original ambition was semiconductor memory. But the deeper purpose was more important. Noyce and Moore wanted a company where innovation would not have to ask permission from a distant corporate headquarters. They had escaped Fairchild to control their own future. What they could not yet know was that the technology destined to define Intel had not been part of the original plan at all. Intel had been founded to replace magnetic memory with silicon. Its first products reflected that mission. The young company built memory chips and struggled to prove it could compete against established electronics corporations. Then a customer arrived with a problem that did not appear to belong to Intel's future. In April 1969, the Japanese calculator company Busicom asked Intel to design a set of custom chips for a new printing calculator. The original plan called for 12 integrated circuits. Each would perform a different function, controlling the keyboard, calculations, memory, or printer. To Intel engineer Ted Hoff, the design looked dangerously complicated. 12 custom chips would be expensive to create, difficult to manufacture, and useful for only one family of machines. Hoff imagined something more flexible. Instead of building every instruction permanently into separate hardware, Intel could create a small, programmable computer. A central processing unit would execute instructions stored in memory, allowing software to control the calculator. The same processor could later be programmed for other machines. Stan Mazer helped Hoff turn the idea into a practical architecture. The proposed 12-chip design was reduced to a family of 4 principal chips, including one programmable processor. But an elegant concept on paper was not enough. Someone still had to fit that processor onto a single piece of silicon. In 1970, Intel hired Federico Faggin from Fairchild. Faggin understood silicon gate technology and had the practical experience needed to transform the architecture into a manufacturable device. Working under intense pressure, he led the physical design of the new chipset. Masatoshi Shima, the Busicom engineer who had helped create the calculator system, came to California and worked closely with him. Together, they converted the architecture into thousands of microscopic connections. The central processor became the Intel 4004. It contained approximately 2,300 transistors, processed information 4 bits at a time, and fit inside a 16-pin package small enough to rest on a fingertip. By modern standards, its power was almost invisible, but the concept was revolutionary. Essential processor functions no longer needed to be spread across boards filled with specialized circuits. They could be concentrated onto one programmable chip and supported by a small family of standard components. The first working 4004 arrived in early 1971. There was still one problem: Busicom controlled the commercial rights. The calculator market had become brutally competitive, and the Japanese company wanted Intel to reduce the price of the chipset. Robert Noyce recognized an opportunity. Intel agreed to return Busicom's $60,000 development investment in exchange for the right to sell the technology outside calculators. Intel had recovered the future for the price of a contract. On November 15, 1971, the company introduced the MCS 4-chip family in electronic news. The advertisement announced a new era of integrated electronics. At first, the market did not fully understand what Intel had created. The 4004 was limited, designed for calculators, and sold in modest numbers. Yet it carried an idea far larger than the product itself. A computer could now be placed inside a machine that had never looked like a computer. Cash registers, industrial controllers, medical equipment, eventually personal computers. Intel had begun as a memory company. Almost by accident, it had created the product that would redefine its identity. But the 4004 was only the beginning. To build an empire, Intel would need a processor powerful enough to escape the calculator and enter the world of general computing. The 4004 proved that a processor could exist on a single chip, but it had not yet proven that microprocessors could become the foundation of an industry. Designed for calculators, the 4004 processed only 4 bits at a time. Intel needed something capable of handling characters, instructions, and larger amounts of memory. In April 1972, the company introduced the 8008, its first 8-bit microprocessor. It could perform a broader range of tasks, but it remained difficult to use. The chip required extensive supporting circuitry, and engineers still had to build much of the computer around it. Federico Faggin believed Intel could do better. The result was the 8080, introduced in 1974. It was faster, easier to integrate, and capable of addressing 64 kilobytes of memory. For the first time, a relatively affordable chip could serve as the practical center of a general-purpose computer. The 8080 did not merely improve the microprocessor, it created a market for one. In 1975, a small company called MITS placed it inside the Altair 8800. Sold mainly as a kit, the Altair had no familiar screen or keyboard in its basic form. Users entered instructions through switches and read results from rows of lights. To most consumers, it looked incomprehensible. To computer hobbyists, it looked like the future. Orders overwhelmed MITS, computer clubs formed. New businesses began producing memory boards, peripherals, and software for machines built around the 8080. Bill Gates and Paul Allen created a version of BASIC for the Altair, giving their young software company its first important product. The personal computer industry was beginning to assemble itself around Intel's processor. But competitors were moving quickly. Motorola, Zilog, and other semiconductor companies offered powerful alternatives. Intel's early lead was not secure. In 1978, the company introduced the 8086. Developed in approximately 18 months, it was a 16-bit processor capable of addressing up to 1 megabyte of memory. Its architecture would later become known as x86. At first, customers were not convinced. Intel responded with Operation Crush. Instead of selling only a processor, its sales force promised development tools, technical assistance, reliable production, and support for future generations. The campaign produced thousands of design wins. One of them changed everything. In 1980, IBM formed a small team in Boca Raton, Florida, to develop a personal computer quickly. Breaking with tradition, the company chose to assemble the machine from components supplied by outside manufacturers. Intel offered the 8088, a version of the 8086, with an 8-bit external data bus. It preserved the new architecture while allowing IBM to use less expensive supporting hardware. Intel also promised the volume, documentation, and long-term support IBM required. IBM chose it. On August 12, 1981, the IBM personal computer was unveiled in New York. At its center was an Intel 8088 running at 4.77 megahertz. It was not the first personal computer, and it was not the most advanced, but it carried the authority of IBM businesses that had hesitated to trust small computer companies suddenly had permission to buy a PC. Software developers targeted the platform. Manufacturers created expansion cards, peripherals, and eventually compatible computers. Every compatible machine increased the value of the Intel architecture. A decision made by a small IBM team had transformed one processor family into an industry standard. Intel had begun by selling memory. Now it was becoming the hidden power behind the personal computer revolution. When Intel was founded, memory was not a side business. It was the business. The company's 1103 dynamic random access memory chip, introduced in 1970, became an early commercial breakthrough. By 1972, most of the world's leading mainframe manufacturers were using it. For a young company, the success was extraordinary. Intel had replaced hand-woven magnetic cores with silicon. Its factories expanded, its revenues climbed, and its engineers continued building denser generations of memory. But memory contained a dangerous weakness. Customers could replace one supplier's chip with another. As products became standardized, price and manufacturing quality mattered as much as invention. During the late 1970s and early 1980s, Japanese semiconductor companies attacked the market with enormous discipline. They invested heavily in factories, improved production yields, and delivered memory chips with exceptional reliability. Intel was no longer competing only against individual products. It was competing against manufacturing systems capable of producing huge volumes at falling prices. The pressure intensified with every generation. Intel would spend heavily developing a new memory chip, only to watch competitors enter the market with lower costs and fewer defects. Prices collapsed, inventories grew. The product that had built the company was becoming a commodity. Inside Intel, the emotional attachment remained powerful. Memory was where Noyce, Moore, and Grove had begun. It was the foundation of the company's identity, its factories, and its technical pride. Leaving it seemed almost unthinkable, yet something unusual was already happening inside the factories. Production managers were quietly deciding which products deserved the limited manufacturing capacity. Memory chips generated weak returns. Microprocessors were increasingly valuable. Without a dramatic announcement, resources began moving toward processors. The organization was changing before its leaders were ready to admit it. By 1985, Intel was trapped in a severe semiconductor downturn. The company was losing money, factories were under pressure, and employees faced layoffs. Andy Grove and Gordon Moore confronted the question they had avoided for years. Grove asked Moore to imagine that the board removed them and hired a new chief executive. What would that outsider do? Moore believed the answer was obvious. The new leader would abandon memory. Grove's response was equally simple. They should walk out the door, return as if they were the new management, and make the decision themselves. Intel withdrew from the DRAM business in 1985. The choice was painful. Production lines were closed or redirected. Projects were canceled, jobs disappeared. Intel surrendered the market that had once made it famous. But it also removed the burden that had been consuming capital and attention. From that moment, the company would concentrate its future on microprocessors. The decision did not immediately solve everything. Intel still faced a weak market, aggressive rivals, and uncertainty over whether the personal computer could continue expanding. But the company had crossed a psychological boundary. It had proven that survival mattered more than tradition. Intel had been created to build memory. To become the processor empire of the computer age, it first had to destroy its original identity. Leaving memory saved Intel. But survival was only the beginning. The company now depended on the processor architecture inside the IBM PC. Every new generation had to remain compatible with existing software while delivering enough power to justify replacing the computers built before it. In October 1985, Intel introduced the 386 with 275,000 transistors and a 32-bit architecture. It offered more than twice the performance of the 286. It could address far more memory, run more sophisticated software, and preserve compatibility with earlier x86 programs. Yet its greatest impact came from a company other than IBM. In 1986, Compaq introduced the Desk Pro 386 before IBM could release its own 386-based machine. The balance of power shifted. IBM had created the PC standard, but it no longer controlled it. Manufacturers could build compatible computers around Intel processors and Microsoft software without waiting for IBM. The architecture had become more important than the company that originally selected it. Intel protected that position aggressively. It intended to lead every processor transition and collect the largest reward. The next step arrived in 1989. The Intel 486 placed more functions directly onto the processor and delivered the speed needed for increasingly visual software. 1 year later, Microsoft released Windows 3.0. The products strengthened each other. Faster processors made graphical software practical. More ambitious software gave customers a reason to buy faster processors. Every new generation of Windows increased demand for Intel chips, while every new Intel chip expanded what Windows could do. The industry called the combination Wintel. Microsoft controlled the operating system. Intel controlled the processor architecture. Hundreds of computer manufacturers competed around them, but these two companies increasingly defined the platform. There was still a weakness. Most consumers did not know who Intel was. They bought computers from IBM, Compaq, Dell, or other manufacturers. The processor remained hidden inside a beige box. Intel decided that invisibility was no longer acceptable. After a successful campaign that marked the aging 286 with a red X, marketing specialist Dennis Carter helped develop a much larger idea. Intel would advertise directly to computer buyers. Launched in 1991, Intel Inside offered manufacturers financial support for advertising if they displayed Intel's logo on their computers and promotions. A technical component became a consumer brand. The sticker on the front of a PC told buyers that its most important component came from Intel. By the end of 1992, more than 500 manufacturers had joined the cooperative program. Then Intel faced another problem. Numbers such as 386 and 486 could not be strongly protected as trademarks. Competitors could use similar names and make their processors appear connected to Intel's success. The fifth generation needed a name that belonged to Intel alone. On March 22, 1993, the company introduced Pentium. The chip contained 3.1 million transistors and delivered roughly 5 times the performance of the 486. More importantly, its name could be remembered, advertised, and protected. Pentium became more than a processor. It became a symbol of the computer age. Intel had started as a supplier hidden deep inside other companies' machines. Now customers entered stores asking for Intel by name. The invisible company had become the most visible ingredient in personal computing, and success on that scale created a dangerous illusion. It made Intel's position look permanent. Intel had conquered the desk. But the next computer revolution would not remain on a desk. During the 1990s, mobile phones spread across the world. Their requirements were different from those of a personal computer. A phone needed to remain cool, conserve battery power, and combine many functions inside a small device. Performance still mattered, but performance per watt mattered more. This was the environment in which ARM became powerful. Instead of manufacturing chips itself, ARM licensed energy-efficient processor designs to companies that adapted them for their own devices. Intel did enter the market. Its X-scale processors appeared in handheld computers, BlackBerry devices, Palm smartphones, and other early mobile products. The company possessed engineering talent, customers, and a credible path into the future. Then, in 2006, Intel sold its communications and application processor business to Marvell for $600 million. Management wanted to concentrate investment on x86 processors, manufacturing, and wireless technologies that appeared closer to Intel's core strengths. 1 year later, Apple introduced the iPhone. The device transformed the phone into a general-purpose computer controlled by touch. As competitors followed, billions of computing experiences began moving away from the PC platform Intel dominated. Most of those devices were built around ARM-based designs. Intel tried to respond. In 2008, it launched Atom, a family of smaller, lower-power x86 processors. Atom became successful in netbooks, cheap miniature laptops that still behaved like traditional PCs. But a netbook was not a smartphone. Reducing a PC processor was not the same as designing an entire mobile system around extreme power efficiency, integrated communications, and custom hardware. Intel announced partnerships, developed smartphone platforms, and promoted Atom as a bridge between personal computing and mobile devices. In 2009, it formed a strategic relationship with Nokia. In 2010, it presented a lower-power Atom platform intended for smartphones and tablets. By then, the ecosystem was moving in another direction. Phone manufacturers already had ARM-based suppliers, software tools, and years of experience. Apple developed its own A-series processors. Android expanded across devices built on the same broad architecture. Intel could produce powerful chips. It could not persuade the industry to rebuild mobile computing around x86. The company spent years attempting to establish Atom inside phones and tablets, but meaningful smartphone share never arrived. Its smartphone-focused processor effort was eventually wound down. Intel remained dominant in PCs and servers. Yet the most personal computer ever created, the smartphone, had grown without it. In 2019, Intel left the 5G smartphone modem business and later sold most of that operation to Apple. The company that once placed its architecture inside nearly every important personal computer had missed the moment when the computer moved into everyone's pocket. For decades, Intel's greatest advantage was not only designing processors, it was manufacturing them. The company's engineers could create a new architecture and build it inside factories that competitors struggled to match. Intel controlled the design, the process, and the production schedule. Its famous tick-tock strategy turned that advantage into a rhythm. 1 year brought a smaller manufacturing process. The next brought a new architecture. For a time, the rhythm looked unstoppable. Then it broke. Intel's 14-nanometer process arrived later than planned. The delay was manageable, but it placed more pressure on the next transition. 10 nanometers became the real crisis. Intel had set an aggressive target for transistor density. Manufacturing the design at high volume proved far more difficult than expected. Yields remained weak, schedules slipped, and products designed around the new process were repeatedly delayed. While Intel struggled, specialist foundries kept advancing. Companies such as TSMC manufactured chips designed by many different customers. Their factories were not tied to one processor architecture or one product roadmap. Every new customer helped spread the cost of the next generation of equipment. The old Intel model had once created speed. Now it created concentration of risk. A delay inside Intel's factories delayed Intel's products at the same time. Competitors gained freedom. AMD could design processors and rely on external foundries to manufacture them using advanced processes. Apple could design custom chips for its own computers and have them built elsewhere. Intel still possessed enormous factories, engineering talent, and revenue, but it no longer possessed an unquestioned manufacturing lead. The warning became impossible to ignore in 2020, when Intel disclosed another delay involving its planned 7-nanometer process, later renamed Intel 4. The company began using outside foundries for more products, an admission that internal manufacturing alone could no longer guarantee the best available technology on schedule. In February 2021, veteran Intel engineer Pat Gelsinger returned as chief executive. 1 month later, he announced IDM 2.0. Intel would continue designing and manufacturing its own chips. It would also make greater strategic use of external foundries and create Intel Foundry Services to manufacture chips for outside customers. The plan required tens of billions of dollars, new factories, and a cultural change. Intel was no longer trying only to repair its old manufacturing system. It was trying to compete with the global foundry industry that had grown while Intel was looking elsewhere. The factories that once made Intel nearly impossible to challenge had become the center of its most expensive battle. Intel had spent decades teaching the world to measure computing power through the central processor. Artificial intelligence changed the measurement. Traditional CPUs were designed to handle a wide variety of tasks with a small number of powerful cores. Training neural networks required enormous numbers of simpler calculations to be performed at the same time. Graphics processors were built for parallel work. In 2006, Nvidia introduced CUDA, allowing developers to use its GPUs for general-purpose computing. 6 years later, GPU-powered AlexNet achieved a breakthrough in image recognition and helped ignite the modern deep learning revolution. Intel still dominated the servers surrounding this new field, but the most valuable work inside those servers was beginning to move away from the CPU. The company understood the danger and invested aggressively. It acquired artificial intelligence startups, including Nirvana Systems in 2016 and Habana Labs in 2019. Intel hoped specialized accelerators could complement Xeon processors and give customers an alternative to Nvidia. Habana's architecture became the foundation of Gaudi. Gaudi 2 arrived in 2022 with stronger training performance and standard Ethernet networking. Then ChatGPT turned generative AI into a global technology race. Demand for accelerators exploded. Nvidia possessed more than fast hardware. It had CUDA, mature software libraries, trained developers, and systems designed to connect thousands of GPUs. Customers could buy an entire platform rather than assemble one component at a time. Intel launched Gaudi 3 in 2024 and promoted its cost, openness, and enterprise performance. The chip was real. The ecosystem gap was larger. A planned successor called Falcon Shores was eventually reduced to an internal test chip instead of becoming a commercial product. Intel was still searching for a stable accelerator roadmap while its rival was defining the market. The pressure reached the top. Pat Gelsinger retired in December 2024 before the transformation he had begun was complete. In March 2025, Intel appointed semiconductor veteran Lip-Bu Tan as chief executive. Tan promised to rebuild Intel around engineering, execution, and customer trust. By 2026, the company's AI strategy extended across Xeon servers, Gaudi accelerators, AI PCs, edge systems, robotics, and manufacturing. Intel was not absent from artificial intelligence. It was everywhere around it. But it was no longer the company setting the rules. The empire that once supplied the brain of the computer now had to prove it could build the machines of intelligence. Intel's story began with two engineers who believed the future should not be controlled by cautious corporations. For decades, they were right. Intel replaced magnetic memory, helped invent the microprocessor, and became the hidden engine of the personal computer age. Its chips entered homes, offices, factories, and data centers across the world. But success changed the company. The empire that once moved faster than everyone else began defending what it had already built. It missed the smartphone, lost its manufacturing lead, and watched artificial intelligence create a new center of power. Intel is not finished. It still has world-class engineers, enormous factories, and a place inside millions of computers and servers. But history no longer guarantees its future. The company must prove that its factories can lead again, its products can arrive on time, and customers can trust its roadmap. In 1968, Noyce and Moore left Fairchild because they refused to let another company decide what came next. More than half a century later, Intel faces the same question. Can it abandon the habits of its old empire before those habits destroy what remains? The answer will not be found in its past. It will be built, one chip, one factory, and one decision at a time.